I have an interesting topic, at least I hope it's interesting for you. It's slightly controversial, as the title says, so async code reviews are choking your company's throughput. But what I'm going to talk about today is my learnings that I had along the way of doing a study that was pretty extensive. It's still kind of ongoing, where I analyzed tens of thousands of pull requests, and some of the insights that I got were expected. Some of the insights that I got were pretty unexpected for me, and I had a lot of learning and along the way. So my name is Dragan Stepanović. I work as a principal engineer at a company called Talabat, sorry, which is part of Delivery Hero. I'm also based in Berlin, in Germany. And over the course of my career, I had a couple of topics that I was really interested in, and some of them have been extreme programming, theory of constraints, lean, and systems thinking. And these years, I'm trying to kind of connect the dots between these worlds, and it's really interesting journey. That's what I can say. I tend to rant on social networks as a bunch of other people, and there's also one fact about me. I don't know if there are any Italians in the audience. No? Okay, good. I put mayo on pizza for some reason. It started at one point, and yeah, now it's kind of almost an addiction. Cool. So then also the thing that I wanted to mention for us today is that I want to frame this talk as a just sharing principle. I don't know if you heard about it, but I'm not saying that you have the same problem that I had. I'm not saying that your context is the same as mine. I'm not telling you that you should do this thing or that thing. I'm just kind of sharing the journey of the study that I had along the way. How many people here heard for this phrase, nobody ever got fired for buying IBM? Yeah, okay. I wasn't part of the industry at that time, but apparently during 80s, IBM was a really huge vendor. And if you were working at a procurement, you had a really tough job not going with IBM because you had a lot of questions to answer, right? So because everyone went with IBM, and what are the reasons for us going off path, so to say. And I also understand this because this kind of gives you a sense of security. Everyone else is going with this vendor, and going with someone else is more difficult because you have a lot of questions to answer. And it provides this, kind of limits this downside risk. If anything goes wrong, right, who could have thought it's IBM? Everyone went with them, right? And the reason why I mentioned this is that when I think about the ways of working that we today have in our industry, this is the visual that they have. So just a show of hands, how many people here do pull requests? Okay, almost all of them. How many people here do blocking pull requests, meaning that you have to wait for someone until the pull request has been approved? Okay, majority still. Cool. So for the folks that are not familiar with the, as I call it, peer-based async code reviews, I'll just walk us through this visual. And here we can see two developers, Emma and Luca. And they're working individually. So Emma is working on ticket number 1, Luca is working on ticket number 2. And if you focus now only on Emma, so she's doing some changes to the code, trying to implement the feature. At one point, she figures out, okay, I think I'm done. So I would like to invite my peers, Luca, for a review. And the way that we usually do that, we raise a pull request and then invite our peers. So she does that, but Luca is busy. So Luca has ticket number 2 that he started working on. There's lots of other things also going on. So there are stand-ups, refinements, reviewing other PRs, checking Slack, email, breaks, etc. And he's not able to respond. Now, Emma, wanting to be a good employee, so to say, and doesn't want to twiddle her thumbs, so she figures out, okay, I'll start working on something else. So she pulls in ticket number 3. Now, Luca is not responding, and Emma reminds him, can you please review my pull request? Eventually, Luca comes around and reviews a pull request. They go back and forth a couple of times because the changes that Luca expected to see were not there. And eventually, they converge on a solution that both of them are satisfied with. the pull request gets approved and then gets merged. So this is the PR-based async code review. Now, I really love this principle. It's kind of guiding principle for me. Meet people where they are, which says that it really doesn't matter where you are currently at. What matters is the trajectory or the direction or the trend. And as long as we're improving and improving at a pace that all of us are satisfied with, that's fine, right? So the reason why I mentioned this is that me having experience in alternative ways of working than the one that we saw, I often got asked by a pretty big share of engineers and engineering managers, that sounds good, whatever you're proposing, but where do we stand today? Like, how can we measure what we currently have and try to improve from there? And that got me thinking, and having an experience in extreme programming, which involves lots of pair and mock programming, which is lots of collaborative programming, I had a hunch about the things that I would be really interested to see when it comes to the async code reviews. So, as I mentioned today, I'll be talking about the study that I started a couple of years back, and it's kind of still ongoing. Over the course of a couple of years now, I analyzed more than 40,000 pull requests. And one thing that is really important to mention here, this is typical product development teams, so no open source software. And the things that I was kind of curious to see along the way, and the things that I kind of had a hunch for, was trying to understand the amount of engagement that I get to see on the pull request. How does that look like compared to the size? What are the wait times that we get to see here, etc. So let's go into the engagement. And the reasons why I was curious about the engagement was that it involves these, I was kind of curious to understand the systemic effects of a delayed feedback, right? So one thing, if there's one thing that I would like you to take out of this talk, is that async equals delays by design. So if you don't have delays, it's not async, right? And if you have async, it means delays. So that got me thinking into, okay, what are kind of systemic effects that we get to see because of a delayed communication that we get to see? And I had this metaphor. It is that when I was having phone calls with someone and there was a delay in communication, what I noticed is that the conversation tends to die off pretty quickly when there's a delay. Okay. So that's one thing. And the other thing that is also important to notice is the way that we provide feedback when we work in async way is through written form, right? So we write some comments on the pull request, ask for some changes, etc. And this way of communicating, or this kind of the bandwidth of this medium is way lower than when we talk together face to face with minimal latency and lots of nonverbal cues that we get to see, right? So that's the reason why I also call this high latency and low throughput feedback. And if we go into the first scatter plot, so here on the x-axis we can see size in lines of code, and on the y-axis we can see the engagement. Now, different people have different ideas about how to measure complexity of the PRs, or as a proxy for the amount of effort that was invested. Some people go with size, some people go with lines of code added, some people go with number of files or packages changed, etc. But what I found for the study was that simple lines of code was a pretty good proxy for that. And then on the y-axis we can see the engagement, and the engagement here is defined as a number of non-trivial comments that we get to see. Now, definition of a non-trivial comment, my definition, is that a comment that is not trivial. And then a trivial comment is a comment that has 4 or less words. Now, why is this important? Is because maybe you share the same experience, but they get to see a lot of looks good to me, LGTM, +1, thumbs up, etc. So these comments don't really provide feedback to the other side. So these are the ones that I filtered out. And what can we see here? Not much, honestly. Most of the PRs are less than 500 lines of code, and most of them have less than 12 non-trivial comments. But that got me thinking. let's say that I invest half an hour and I produce a pull request of 50 lines of code and I get 2 comments back, right? And let's say that I invest a week, I produce 1,000 lines of code and I get 2 comments back, right? So the amount of comments that I get, I'm not going into the quality of the comments, but just the amount of communication that I get to see back and forth, depending on the size, is something that that I was really curious about to see. So what happens if we normalize the y-axis? Let's say that the y-axis now is engagement per size. So if you look at the spectrum of the size of the pull request, how does engagement per size look like on that spectrum, right? And that's where things got interesting. And this is something that honestly I expected, and we'll go into that in a couple of minutes. But what we can see here is that as we increase the size of the pull request, the engagement per size drops a lot, right? So we get a way less comments per 100 lines of code. Even though I would say for a bigger pull request, I would expect to have way more comments. In a sense that there are more things to go wrong, so to say, right? And this is really interesting because we are using async code reviews, or at least most of the teams that I work with, as a way to build in quality through human judgment, right? From inviting human judgment. But now we're saying that on the bigger size of the pull request spectrum, we see way less engagement and way less feedback, and because of that, we're also not able to build the quality in, because our assumption was we're building quality in by building in human judgment, and if we're not able to see that, then also we have trouble with being able to build the quality in. Now, I'm not saying anything about the left-hand side. I'm not saying that if you have more comments that there's more quality, right? So it really depends on the seniority of people, domain knowledge, and all these things. But what I'm just saying is that if we don't have ability to provide feedback to the amount that we expect to see or we expect to have, then there's also less ability to build the quality. Okay. And talking about that this seemed intuitive. I think that lots of us kind of experience this, and that's the reason why I also really love this quote. Never had a huge pull request that didn't look good to me. So apparently all big pull requests look good to us. And probably lots of you have seen these 10 lines of code, 10 issues, 500 lines of code. Looks fine, right? So code reviews. The other day I also ran into this video from, I'm going to have some trouble now trying to pinpoint here. So you can see some stewards here trying to prevent people from entering, right, the field. And this is, I think, the way that reviewers on a big pull request feel like trying to build the quality in, right? So the thing has already been done. If I get a pull request after 1 week, or 1,000 lines of code, or 500 lines of code, or even 300 lines of code, it's already done. The quality is either there or it's not. And let's go now into the wait time. So wait time was a part where there were kind of interesting surprises for me. And the way that we think about the wait time, if we look here at ticket number 1, so at the bottom of the screen, you can see the, so to say, life cycle or the lead time of ticket number 1. And we can see there are some yellow areas and some gray areas. And the yellow areas represent when we're actively working on this item. So Emma is coding, or Luca is reviewing, or Emma is incorporating feedback from the comments, etc. And gray area is the wait time, and the wait time represents where this, at the time during its lead time, where this thing is just sitting there waiting for someone's attention, right? So Emma asks for a feedback, Luca is busy, and this is the wait time, right? And the way that I calculated wait time, I use approximation as anything that we try to measure when we try to measure something in software delivery. And this approximation also has some assumptions. But the way that I went about it is that we usually pick up an item, start working on it, and then at one point we think we're done. We try to invite feedback, and from that point on, the clock starts ticking. So this is a wait time. Now, if I get to see lots of comments or I get to see lots of follow-up commits after that, this approximation is not as good. So that's one of the things to have in mind. There are a couple of other assumptions when it comes to this approximation, but I'm not going to have time to go through these. The point is just that we have to be aware that any approximation has some assumptions. So how did the results look like? And these are the typical results that we get to see. So this is a data set of 500 merged pull requests. And for this team, it took them 6 months to push 500 merge pull requests through the system of work. Now, what was interesting is that the cumulative wait time, meaning the time that wait time per PR accumulated, summed up, was close to 28 months, right? So you had 6 months of dedicated to pushing these 500 pull requests through the system of work, and the amount of accumulated wait time where these things were just sitting there waiting for someone's attention was close to 28 months, right? I'm not saying that these numbers are precise, even if they're 50% correct, they're a really, really good conversation starter, right? So it's just about the magnitude of these. And the reason why this is important, so I'll try to connect the dots for you, why wait time is important for product development, right? So I hope that all of us are here because, and also work at the teams that we work at to deliver value to our customers, right? So, and delivering sooner things in production, experiments, trying to learn sooner is something that help us or is necessary in order to be able to deliver value sooner, right? So we want to iterate faster. And the way that they also think about it is we want to have this fast learning cadence, right? And I'm not sure how many of you have played this game when you were kids, Hot and Cold, where one person hides an item, looking for it. And the person that has hidden the item provides a feedback to the other person every couple of seconds or so. And as you get closer to the item, the temperature increases, etc. But why this metaphor is important for us is that imagine that you have two teams. One team is able to get the feedback after every minute, and the other one is able to get the feedback every second. On which of these two teams would you bet that they're going to find an item sooner? So I'm pretty sure on average you're going to bet on the second one, right? It doesn't have to mean that they're going to win all the time, but on average they're going to win. So that's the reason why it's important to think about the learning cadence and what does this wait time, which means that the value being stuck in the system of work, not being released to the customer. So all of the learnings are kind of stuck in our system of work. That's the reason why this is very important. So let's look at the scatter plot for the wait time. And here we can see, again, x-axis size, lines of code. In the y-axis, we can see wait time in hours. Again, not much to see here. Most of the pull requests have less than 200 hours of wait time, which is huge, but let's not talk about it now. In any case, that also got me thinking, let's say that I work for a week and I produce a pull request of 1,000 lines of code, and then I wait 2 days for the review. It's not the same as when I work, say, half an hour or 1 hour, and I produce 50 lines of code and then I wait 2 days for the review, right? So the relative cost of code review in these two cases is different. So what happens if we normalize the wait time now by size? Well, if we do that, now on the y-axis we have wait time per size, which is in minutes per lines of code, and things get interesting here. And what we get to see is that and this is the thing that shows in all of the data sets for the teams that have been doing async code reviews. So all of the things that I'm talking about today were present in all of the data sets, which kind of points into the systemic direction of the problems. So as we increase the size of the pull request, the wait time per size drops exponentially. As we decrease the size of the pull request, the wait time per size goes up exponentially, right? And the way that I interpret this is that as we reduce the size of the pull request, the cost of code review per size goes up exponentially. And this is kind of a system pushing back against us. So we want to have small PRs, right? Everyone, I would assume here, wants to have smaller PRs. But then we're incurring a way higher costs of reviewers in these cases. And another way to think about it is that the reasons, or kind of, if we iterate through the reasons why we want to have small PRs, and this is the idea that is coming from Lean, small batches, anyone that has heard for that. So small PRs are really important because they take less time to write, quicker to review, so also less time allocation for the reviewer. I can easily fit 10 or 15 minutes of a review instead of having to review at 1,000 lines of code a couple of hours, right? They tend to have higher engagement, as we also saw for the smaller PRs. They're also less risky because less things changed, right? And then when things go wrong, it's also easier to troubleshoot because there's a smaller haystack to find a needle in. And also when it comes to the DORA research, they also contribute positively to all of the 4 metrics for the DORA: mean time to recover, lead time to change, deployment frequency, and change failure rate, right? But again, with async code reviews, the system is pushing back. We want to have smaller PRs, but the costs are getting exponentially higher. And I'm pretty sure that most of us here experience this in some other scenarios. Let's say that we have a test suite that takes 20 minutes to run. If I have a test suite that takes 20 minutes to run, I'm not going to run it after every line of code change because it doesn't make any economic sense, right? Because most of the time I'm just going to sit there, wait for the test suite to finish. So what the system is telling me is, hey, the cost of running test suite is really high, use it very wisely. So I'm going to increase the amount of changes that they introduce to the system before running the test, which means the system pushes me back into the bigger change set or bigger PRs, so to say. And this is a problem because we don't want to be in this part of the spectrum, as we said. This is kind of an invitation for you to think about the economics of the system that you have at your companies and your teams. And for that reason, I really love this quote from Don Rynerston. While you may ignore economics, it won't ignore you. Another thing to also to have in mind is that try doing small changes and asking for a review in this kind of environment, right? It's probably not going to happen because I would have to, again, spend most of the time just waiting, right? And this is problematic because I think this is the reason why I think that teams that have lower latency in their communication tend to produce way healthier code bases because they have ability to do continuous refactoring more often, which means that we keep our code base healthier and more responsive to change. Okay. So I was trying to make also sense of the reasons why teams doing async code reviews were not able to continuously decrease the size of the pull request. And here we can see this is called the causal loop diagram from systems thinking. You might also find it useful for some other cases, but I'm also going to give you a short crash course on the causal loop diagram. So it consists of variables. So here we can see PR size, motivation, where it's set to review, number of interruptions, etc. And then we connect the variables. We can connect them in 2 ways. One way is they move in the same direction, which is color coded as blue, which means that when one variable goes up, the other one goes up as well, and vice versa. And there's the opposite causal link, which says that when one variable goes up, the other one goes down, and vice versa. Now, when you start connecting the dots and start connecting variables, you might discover some loops. Now, there are 2 loops that are available or present. So one is a reinforcing feedback loop and the other one is a balancing feedback loop. Now, reinforcing feedback loop is kind of well known. It's kind of the snowball effect. So the more of something you have, the more of it you have. And the balancing feedback loop is the loop that seeks kind of goal. So if we have a thermostat here set at 21 degrees, the heating system or the cooling system is going to work until it matches this temperature to the room temperature, right? If we open up the doors, the heating system is going to work even more until we reach this temperature, and then it's going to stop. Okay. So let's go through the causal loop diagram. So, and I'll try to tell a story, right? So again, context, async code reviews, trying to reduce the size of the pull request. Let's say that we halve the size of the pull request. The motivation or incentive to review goes up because we're more likely to review a smaller pull request than bigger pull requests. And when that happens, also time waiting for a review from author's perspective goes down, which is a good thing to have. and the perceived cost of code review per line of code goes down. Now, if this perceived cost of code review per line goes down, it also incentivizes us to keep reducing the size of the pull request. And this is the reinforcing feedback loop that we have here, and it's kind of a desirable one, the one that we want to have. But it's not the only thing that is playing out in this system. Because if you reduce the size of the pull request, then the number of PRs to review in a unit of time goes up. So if I had a pull request in 1 week and then I halve the size of the pull request, I'm going to have 2 pull requests. Now you might multiply that by the number of people that you have in the team, but you get to understand how much the number of pull requests to review in a unit of time goes up. And because of that, also number of interruptions for the reviewers as you push or as you increase the number of PRs to review, the number of interruptions also goes up. And this is a problem because everyone wants to keep their flow, right? So we don't want to get interrupted as often. And so the motivation or incentive to review goes down, and time waiting for a review goes up. Perceived cost of code review goes up, and that pushes us back into the bigger PRs. And so that's a balancing feedback loop. It's kind of preventing us from this reinforcing desirable behavior we want to have. And again, that's not the only thing that is going on, because also when there's an increase in time waiting for a review, what happens is that, by the way, you can see that the conflict is here, right? So this variable is pushed from 2 different sides. But when the wait time for a reviewer goes up, then temptation to start working on something new also goes up. So you saw it also with Emma. While she was waiting for Luca, she pulled in another thing, which actually, again, increases even more the PRs to review and prevents us from desirable reinforcing feedback loop that we want to have. So that's kind of a story when it comes to ability to reduce the size of the pull request in the async code reviews and the things that are pushing back against us. Now let's switch gears and talk about the flow efficiency. And flow efficiency is a metric coming from Lean, and it's trying to understand, when you look at the lead time of an item, how long do we spend working as a percentage of the lead time. So if you have a higher number for flow efficiency, that means that your process is better than when you have a lower flow efficiency. Lower flow efficiency means that you have more wait time in the system, just things being stuck, waiting for someone's attention. So I try to measure this, and on the y-axis you can see, you can treat it as a flow efficiency. I won't have time to go specifically into this metric, what exactly it means, but you can treat it as a proxy for the flow efficiency. And as you can see here, it starts plummeting at one point. So for this data set, it started plummeting around 120 lines of code. And the numbers are not as important. What's important is the shape of this curve. And when we think about that, and let's think about a thought experiment. Let's say that you have a 300 lines of code change that you need to push through your system of work. And let's say that you have at least 2 ways to do it. One is splitting these 300 lines of code into 15 PRs of 20 lines of code. And the other one is just having 1 PR of 300 lines of code. Now, what this curve is telling us is that the cumulative lead time that is going to take us to push 15 PRs of 20 lines of code is going to be way longer than the cumulative lead time of 1 PR of 300 lines of code. Okay. What does that mean? It's that actually we're losing throughput on the smaller size of the PR spectrum. And the reason for that is because we have higher wait time per size, and that leads to longer lead times, and the longer lead times lead to lower throughput. And one way to think about it is that when you work asynchronously and you reduce the size of the pull request, one thing that is really interesting is that the processing time, like how long does it take you to produce a PR, review it, etc., usually goes down, right? But what's important is that as we reduce the size of the pull request, we are inviting dependencies more often and sooner, meaning because we're dependent on the reviewers, right? And because of that, we are incurring the costs of dependencies, which are really high, more often. And that's something that drives the wait time to processing time ratio up because the wait time starts dominating the lead time, and that hurts the flow efficiency and the throughput. So one funny thing also to mention here, I don't know if you noticed this one, which says, "Can you review my PR, please?" And these begging hands. How many people have saw this in their Slack channels? I'm not sure, but I noticed over the years that people have different ways to beg for, reviewing the pull request or asking for a review. And what I noticed is that the teams and that have a lot of work in process, that they're doing too many things at the same time, tend to have way more begging. Why? Because the system is unresponsive. So everything is stuck. And these are kind of crying calls to try to move the things. But the problem is not there. It's not about responsible developers. It's that we have too many things that we're working on at the same time. Okay. So there's a reason why I say that the amount of begging in the system is proportional to the working process. So the more working process you have, the more begging you'll get to see. But this is system telling us something. So this is a feedback that we try to listen to. Okay, so from one side we're saying that we're losing quality, or we're less likely to build in quality with the bigger PRs because we're losing engagement, which is a precondition for us being able to build the quality. And then on the other side, we're losing throughput on the smaller end of the spectrum, right? So we need to balance between these two forces, and we have to get to choose: we lose throughput or we lose quality. And for anyone that had a chance to read the book from Don Reinertsen, this is called Batch Size Optimization U-Curve. And this line here, the overall cost, so we're trying to balance between the two forces, and we're trying to find a sweet spot there. Right? And this curve is telling us where is the optimal batch size, having these kind of forces that we have in the system, and then we're trying to find the optimal batch size. Sorry. And I get to hear this often, and me growing as an engineer, I used to say this more often. There's always a trade-off, and it depends, and all of these things, right? For some reason, that says something about your seniority, I don't know. But what I found along the way is that it's not really true. So there are some trade-offs that don't exist because the underlying assumptions are flawed. So when we talk about the trade-offs, we also have to think about what are the assumptions that are behind those trade-offs that we're talking about. So just curious, how many people here have had a chance to read the Accelerate book? Cool. So Accelerate book kind of presented the results of the DORA research, which was, I think, a 5-year study. Really important one. This book came out, I think, in 2018, and it's, I think, one of the most important books we had in our industry for a very long time. And the biggest myth that was debunked, at least for me, was this idea of throughput versus stability when it comes to DevOps, but in general, idea of one versus the other one, right, in this case. So the results of the research was, or one of the results was that you either have both of these, both throughput and stability, or neither of those. So what I'm saying is that we might have our cake and eat it too. Okay. So what I'm going to do now is I'm going to walk us backwards, and we're trying to start with the problem that we have, and we're trying to figure out what are the alternatives that we might want to consider in order to reduce the undesirable effects that we get to see. So the cost of code, we're saying that if the cost of code review per size is going up, what we get to see is also the throughput plummets as we reduce the size of the pull request. But we want to have small pull requests, and we don't want to lose the throughput. So how can we go about it? So if we want to keep the throughput, then the cost of code review per size must not go up. So it needs to stay constant, or needs to stay minimal, right? Because if it goes up, the throughput plummets. And in order for us to not increase higher cost of code review as we reduce the size of the pull request, The actors' reaction time, and when I say actors in this process, I mean authors and reviewers, their reaction time needs to be exponentially faster and faster and faster as we reduce the size of the pull request, which means they need to react faster to each other's request. Now, in order to be able to do that, their availability needs to go up as we reduce the size of the pull request. It needs to go up exponentially because if you remember, Luca would like to respond to Emma's request, but he's busy with a bunch of other things going on, right? So if we just pull up ticket number 1 here, and the same thing is happening with other tickets. So if you pull up for ticket number 2 or ticket number 3, you are also going to see lots of the wait time. So if you have lots of things that you're working on, the wait time starts dominating the lead time. So most of the time, the item is spending just waiting for someone. Okay, completely unproductive. So if we pull up ticket number 1 and we say, look, and Emma have this size of the pull request and they want to keep reducing it while not losing throughput, they as they reduce the size of the pull request, in order not to lose the throughput, they will have to react faster and faster and faster to each other's request until at one point they start probably working together. Because raising pull request doesn't make any sense. Sorry. And this was the conclusion of the study. So in order not to lose the throughput exponentially as we reduce the average size of the pull request, people need to get closer and closer and closer in time, and this leads us to a continuous code review. Now, if we look at the motivational incentive to review here, again talking about the assumptions, so we had a problem because we had lots of interruptions for reviewers, right, as we reduce the size of the pull request. But I'll take a sip of water. Not as funny as I thought. But if we're working on the same thing at the same time, and you ask me about this thing, you're not interrupting me because I'm working on the same thing, right? So this conflicting point is kind of removed, and this leads me. The continuous code reviews leads me to a parallel universe, as I call it, which is at least I call it co-creation patterns, pair and mob programming. And just by show of hands, I'm kind of curious how many people here had a chance to do pair and mob programming. Cool. Keep your hands up if this is the default way that you work in teams, meaning at least 70% of the time you're doing that. Okay, no one. Cool. But today I'm just talking about one of the aspects of working together. There are lots of other really, really beneficial things that come up as a byproduct of working together: psychological safety, vulnerability, increased throughput, etc. But I'm not going to talk about that today. I'm inviting everyone to try this out, right? And the interesting thing that happens is that continuous code reviews that we need actually come as a byproduct of the way of working. Because when we're working together, you get a review after every line of code change. And it's really, really cheap because you have it immediately. So the latency is 0, right? And another thing to think about, how does it affect the economics of the work? It's that actually we reduce the cost of a review because the availability is immediate. What that means is that transaction cost, this is from Lean, but you can treat it as transaction cost, is pushed all the way to the left, which means that the optimal batch size can now be moved to the one extreme end of the spectrum, right? So you have one line of code review, so to say. And so looking at this wait time per size, by size scatter plot, I thought, okay, how would this scatter plot look like had we done continuous code reviews? So the wait time will be 0, again, because availability is guaranteed, is a byproduct of the process. And the engagement per size, I don't know, but what I noticed is that people, when there's a lower latency in the process, there's tend to be way more engagement. And then I started thinking, okay, so what are we trying to optimize here for? So we want a smaller size, we want smaller wait time per size, we want engagement, not to lose engagement per size, right, as we reduce the size of the pull request. So you might have noticed this bar here, which is color coding this metric, which I called PR score. And the way that they calculate it is based on these three things that we were optimizing for here, and that is size, wait time, and engagement, right? So we want size to go down, we want wait time to go down, and don't want to lose engagement. Now here we're dividing by 1 plus engagement. Why? Because engagement can be 0, because we might have 0 non-trivial comments, and we don't want to divide by 0, right? So, and then the smaller this number, the closer to 0, the better result you have, right? Because these are the directions of these metrics that we optimize for. And then I started thinking, okay, how does this thing look like when we build together, we do co-creation, pair mobbing, right? So the size of the pull request can be as low as 1 line of code, because you have a continuous code review, right? Then the wait time in minutes is 0, because you have immediate feedback, and the engagement, I don't know, maybe goes up, maybe stays constant, but doesn't matter. What's important is that this thing evaluates to 0, right? So you get as a byproduct of the way of working the results that you desire. And that's the reason why I also tend to say that the optimal size of a pull request is 1 line of code that is reviewed as it's being typed, so to say. And I think in the industry we are still looking for better ways, but this is the best thing that I found yet if we're optimizing for these things, which is pair and mob programming. I think all of us need to be open for discovering other, perhaps better ways, but I think this thing is looks very, very promising. I would say for a very long time will be the case. Now, having said that, and if you look at the PR score, so this is a data set, I think 500 pull requests or so. So each of the dots represents a pull request, and then on the y-axis we can see the score. Now the score here is on the log scale because the results were so high, meaning so bad, that they had to use a log scale in order to do that. So this is one world that they get to see. And then there's the other world that they get to see, which is continuous code review with pair and mobbing. And this is the distance on the log scale between these two universes that they get to see. Now, sharing something from one of the teams that is doing extreme programming, and when I say that, I think there are a couple of things to mention here. So it's not only continuous code reviews through pair and mob programming, right? So it's, yes, mob programming as a default, but also continuous refactoring, great design skills, TDD, etc. And the team is not using any pull requests. They are pushing straight to trunk, because they're able to build the quality in before they raise a pull request, because all of the things happen before that. So one day I was really curious to see how do we look like when it comes to the frequency of integration. And for this team, what they discovered was that we had, in a time span of 9 hours and 20 minutes, and I think it was 5 engineers, or maybe 6, something like that. But in a time span of 9 hours and 20 minutes, there were quote unquote 107 quote unquote PRs merged to the trunk. So this level of frequency is completely different world than what they get to see, which is usually like 1 pull request per day, or a couple of those, or 1 in a couple of days, etc. But the median time to integrate, so from the start of the commit until the commit was on the trunk and in a deployable state, was 2.3 minutes. And this is something that comes as a byproduct of the way of working. No one was trying intentionally to do this, right? So I just figured out that one day, I'm really curious how this thing looked like when we mine the Git log, and these were the results that we got to see. So kind of no PRs, no async code reviews, and trunk-based development as a byproduct of the way of working. That's kind of that was kind of the idea. So throughput or quality, I would say both throughput and quality. I think we have to think about the assumptions that we have when it comes to that. And with that, I would just want to say and close with we've been told all along that we'll have that we'll achieve more if we delay and limit our interactions. But I also hope now that you have a data-informed reason not to believe so, right? And invite you to try exploring some alternative ways of working, so to say. A year ago, I wrote an article for InfoQ that got quite a lot of attraction. And I think the reason for that is that there is a need for, I think, for this conversation in our industry. for some reason we adopted this idea of pull requests from the open source world, which is completely different context than the way we work in the typical product development teams. And I hope that this talk today helps you with trying to understand why it's worthwhile maybe exploring something else, and hope that you have luck with that. And with that, I would like to finish for today and invite any questions you might have. Yes.
One programming didn't work for us. We tried, and it didn't work because it was difficult to concentrate as a developer when around me there were so many people. And switching keyboards was interrupting us. So what we have tried, and the question is, if you have never heard of it, is mob code reviews. So we do the pull request,
Yes.
we're gathering,
Yes.
we do the code review
Yeah.
together, and then each one has some minutes to review the code. Small PR is always
Yeah.
the main thing, but
Yeah.
I haven't read it. We tried that. I don't know if there is research on this, or something else. So.
Yes, I think this is a good progression from the async code reviews, doing reviews synchronously at least, before we go into that. But there's one question I wanted to ask you. When you said that you tried mob programming in your team, was there anyone in your team that had experience with mob programming beforehand? Yes. That's the thing that usually happens, because these skills are learnable and we don't have, they're very scarce. It's very hard to find people that had experience with these things. So what ends up is that we end up with teams being very excited of trying to do these new practices, but having no proper guidance, facilitation, etc. Some coaching, so to say. And what my experience tells me is that these teams end up not going into this direction because they don't like what they experienced, but the thing that they experienced was nothing related to mob programming and pair programming. They were doing something else, even though they don't even know or are not sure that they did the right thing, so to say. So it's not just let's jump on a call and let's hijack a keyboard, or driver takes a keyboard and goes into their own direction, everyone zones out. This is not mob programming, right? So we have to be really sure that we're evaluating the thing that we think that we're evaluating, right? So that's one thing that I usually advise for teams that are starting out with this. If you don't have anyone in the team that has good experience with these things and is able to coach you and facilitate and guide you, then you have to be really careful about, you can still go about it definitely and learn as you go, but to make sure that, always asking ourselves question, are we evaluating the thing that we think that we're evaluating, right? Maybe there's something that we're doing wrong when it comes to this, but yes, definitely mob reviews are good progression from there, although there's also a problem with that, because it again has the problem of not being able to synchronize everyone, because everyone is busy with something. And then when there is async work, it's very hard to synchronize, to get people. Yes. No, well, yes, but what I meant is that, you finish your review, there are 3 of us, but all 3 of us are working on something else. And you ask us for our time, and we're busy with something else. And that's the thing that is hard with the async system in a sense, to trying to get into the sync mode at that point. I don't think it's not feasible, I just think it's harder in that sense. That's kind of an idea. Cool, and there we have one more question there.
Thanks a lot for the talk. Really very thought-provoking. Sorry. I wanted to reflect on those images that you showed in the beginning, when the ladies were standing, making the row and trying to stop a guy, What made me think about is that probably it's about long expertise of the reviewer, right?
Sorry, I'm not sure what slide you were referring to.
Do you remember when there was a football field?
Ah, yes.
There were ladies
Yes.
standing and the guy just passing. So you talked about having like a person who works on the same thing. But what made me think that picture is that probably we need to think about reviewers who have sufficient expertise to review the work. So I was wondering your thoughts about it.
Yeah, I think that definitely plays in, and I usually get asked, okay, even if you do reviews, like who would you invite for a review? I think that's very context specific. And it's like we have a senior engineer that knows this part of the system the best, and they're the bottleneck, so we have to wait for them, etc. And how do we make sure that two juniors are not working together? Meaning, I mean, if they don't have enough knowledge, so they have to invite someone. But what I find when it comes to working together and co-creation patterns is that we have this bottleneck, and it's there, right? We cannot go about it in like we cannot remove it just like that. But how do we accelerate this missing knowledge through the team sooner? And working together really helps with that, disseminating this knowledge, like this engineer that has the most knowledge about the system becoming a deliberate bottleneck, the bottleneck that we want to have in the system in order to spread this knowledge sooner, so we can make them less of a bottleneck as we go, right? So that's kind of the way that I'm thinking about it. But yeah, I'm not sure also if I'm answering the right question. That's one thing. I think I'm touching upon what you asked, but the other thing is also I completely agree that it's also really important to factor in the seniority of the people that are part of the session or reviewing the PRs, and how do we go about it in order not to lose quality. It's not just working together, but also taking into account the expertise and the experience, etc. Thanks. Okay.
So in the whole graphs measuring throughput, which was not made very visible, is that when you pair mob programming, that you have n persons working on the same thing, which then divides productivity per person.
Yes.
So that was not very visible.
Yeah, yeah. So in theory of constraints, there are two things that are really important. One is the constraint management. The other one is the cost accounting versus throughput accounting. And why I mentioned this is that we have to really think, the way that it translates into this talk today is that we have to think of the things that we're optimizing for. We are not optimizing for keeping everyone busy and reducing the cost of people. We're optimizing for delivering value sooner. That's the thing that brings us money, hopefully, right? So how do we, that's the first thing that we optimize for. We might optimize for utilization, but only after that. That's not the first measure that we're optimizing for. Meaning that we want to reduce the lead time of delivering and learning and experiments, etc. And only if you figure out that we have like too many people in the session or not everyone is needed, that's fine. But that's the optimization that comes after the first one, which is the one that we're trying to optimize for. So it's kind of a paradigm shift, so to say. It's a different thing, different lens through which we're looking at the work, so to say.
So are you saying you're optimizing for lower latency, but you're accepting reduced bandwidth, basically?
So what happens is that when we reduce the lead times, the throughput also goes up, because the things are stuck less in our system. We start, as you saw it also with this continuous integration thing that I showed, things get churned out from the system sooner. And I'm not saying that like the multiple teams need to work at the same time on the same thing, but this is not, thinking about the cost is not the first thing that we're optimizing for. The cost is usually coming as a later
I'm not
thing.
challenging that. It's just like in the graphs, it wasn't visible, like what is the factor that you have then multiple people. I mean, let's say you have a team of 10 people, and you need to produce some value. And since there's this limiting factor of you have 10 people, then you need to take it into account in the calculation somehow, which then might lead you to an optimal mob size.
Yeah, yeah. So this is a question about the mob size and what are the skills that you need in order to get this thing from start to finish. So that's a topic that is one of the topics to discuss when we go into a mob session, and that's usually what I'm asking. What are the skills needed in order to get this thing from start to finish? So this is the minimal number of people that we need to have, or minimal number of skills, right? And then if we see that we have more than needed, that's fine. Okay, maybe we can have one more mob besides that one that we have in a team. So mob is like more than 3 people in general. That's kind of the idea of a mob. It doesn't have to mean the whole team. Cool.
Thanks.
One more question. There's one more question here.
Thank you. So you mentioned that you push directly to develop or to the trunk, as you said. Do you even create any pull requests anymore, or is it just pushing commits to the trunk, right?
Yes, this is trunk-based development.
Right.
Yes.
Right. I just wanted to.
Yes. No
okay.
pull requests. I mean, there are unofficial branches, so these uncommitted changes are an official branch, but there is no pull request. There's nothing officially in that sense.
Right.
So
That's it.
yeah.
Short question. Thank you.
Okay, then thanks for joining, and wish you a great time at the rest of the conference.